Everyone, so this is the second topic of our seminar series where we are discussing on the global analysis from various experiments. So today we have the global analysis from LHCb by Boente. And the general rule is that we have about 1 hour for the speaker to talk, and then we take the question and answers at the end. So unless you have any pressing or urgent question, then you can simply either raise your hand or speak up. Otherwise, you can put your questions in the chat window, and we will keep track of it, and we will go through them at the end. So, Oscar, I think now you can take it over and start your seminar.
Okay, very good. So first of all, let me thank you all for the invitation. It's very nice to contribute to this series of very interesting lectures, and well, I hope I represent well my collaboration at LHCb. So first, this is a bit the outline of my talk. So I will start a bit contextualizing the collaboration, although you probably know about this, and talking a bit about the LHCb detector and its particularities. I will go brief because there was already a previous lecture about LHCb, but I think it's interesting to focus some of the systems, let's say, that are interesting for later. Then I will move more to the topic, to heavy ion physics. I will give a very, very brief introduction because it was already very discussed before, and I will move fast to the main topic of how do we do to characterize globally heavy ion collisions, and how do we determine centrality at LHCb. Then I will move to small systems, which is actually the core of the physics program of LHCb, but it's also relevant for heavy ion physics. And I will give some illustrative results of global analysis or measurements, trying to avoid those already covered in future lectures. And finally, if I have time, I will give you a few words on the LHCb upgrade. So yeah, if there are questions, urgent questions, you can interrupt me without problem, but in any case, there will be the discussion session as it was mentioned. So yeah, you already know this. LHCb is one of the 4 main experiments located in the Large Hadron Collider. We are here in the Boente in the French part. And basically, for the last 10 years, more or less, during round 1 and round 2, we have taken data of colliding protons on lead nuclei and also lead nuclei together. So, yeah, this is a sketch of our detector. LHCb is a forward spectrometer, fully instrumented between 2 to 5 units of pseudorapidity. Originally, as you might know, this design was aimed to collect the largest possible statistics of big hadrons. But as you will see, this geometry also gives us capabilities for very interesting measurements in heavy ion collisions, for instance. So basically, I will talk briefly about the tracking system, particle identification systems. This was already actually the topic of the previous lecture. And just to mention about the trigger, we are generally aiming to measure more lower momentum particles, more like ALICE, and as opposite to ATLAS and CMS. So one of the collision modes that we have at LHCb, this is what we call collider mode. So basically here we standard data taking as for the other experiments. There are, if we in LHCb 4 configurations, let's say, that we can have proton-proton, lead-lead, and then for proton-lead, we can reverse the direction of the beams and access both forward and backward regions. Okay, so basically about the data taking in PP collisions and at LHCb, we are leveled our luminosity. So we have only around one interaction per branch crossing, so mu is 1. However, as in other experiments, P-LED and LED collisions, mu is much lower than 1. So we only have one interaction at most in our events. Some technical details in proton-lead, the energy of the beams are different because of the configuration of the LHC magnets. You have here the relation. Basically, this means a boost in the center of mass system of 0.5 units of rapidity. And also an important point in this talk is that with the more lead we have in our collision, or the larger the ions that we collide, the larger the detector occupancy, and this will impact our performance. So apart from the standard collisions, at LHCb we have a special configuration which allows us to get fixed target collisions. So this is achieved with the smog system. So basically we can inject gas in this detector here, the Vertex Locator, and this allows us to record collisions of one of the beams that come this way with the gas at rest. So this is used both for measuring the luminosity of the beams, but also for physics measurements. So far, we have injected novel gases, and due to the configuration, the energy in the center of mass system it ranges these values here, which is interesting because it's between the energies of SPS and RIC experiments. So also the rapidity in the center of mass system changes, and now in this range we cover between -3 and 0, so between backward to central region. And we can even determine the luminosity, so we can measure cross sections thanks to the calibration with proton-electron elastic scattering events, which is very, very interesting. So during these years, we have managed to collect these data sets that I show here. So we have here proton-lead and lead-lead data sets. For lead-lead, our most significant data set is the one we collected in 2018, the same as P with lead neon, which was actually taken simultaneously in the same RAM. And for a fixed target, we have several samples that we took all over the years. For PP, we have very large statistics, and we have even different a variety of energies. And you have here our total luminosity, which is about 9 inverse femtobar. So I will talk briefly about some of the detectors. So first, I will mention the Vertex Locator because it's interesting for our business here. So the Vertex Locator is a silicon microstrip tracking detector that is around the interaction point. So basically, this would be 1/2 of the detector, and the beam would be around this area here. The detector is able to close and open, so it allows it to be only a few centimeters to the beam, and this can only be done during a stable beam. So it needs to have this capability. And this closeness to the beam is with the aim to have the best resolution to reconstruct the primary vertex, so where the interaction takes place, but also secondary vertexes of heavy flavor decays, basically. And also the tracks that reconstruct are used for the seed for track reconstruction, as we will see. This detector is important also because it has the largest coverage in pseudorapidity, even in the forward as the rest of the detector, but also in the backward region. This will be thanks to these backward stations here. basically, when we are in collider mode, the interactions would be located in this region, more or less. But when we inject gas, we will have interactions all over the Velo vessel, and this is an important point that we will have to consider. So apart from the Velo, we have another two sets of tracking stations. So they are located before and upstream and downstream dipole magnet, which you can see here. This would be the upstream, and here you would have the downstream. This configuration allows us to reconstruct tracks and measure the momentum of these charge tracks. Most of the physics tracks are these long tracks which have hits in all the detectors, but there are other kinds of tracks that can be used for different purposes. Another point I want to make here is that this is a sketch of a typical PP collision at the LHCb. So you see that the occupancy is already considerable. It's quite hard to do tracking over these distances, and the detector is optimized for mu1. So this has a problem that is when we try to go to central lead-lead collisions, we reach saturation in 60% most central collisions. So this saturation is actually happening in the Velo, which is where the first problems start. Actually, well, this slide is about the PID. You already heard about this, so I won't stop here very much. Just to mention this plot here on the bottom, that you have the number of Velo clusters versus the equal energy. So this plot shows us that this is in lead-lead collision. So we want to see how much of this saturation and where it starts to happen. So you can see that around 10,000, only for very low occupancy, we have kind of a linear behavior, but then the number of Velo clusters start to reach this plateau, and this makes tracking impossible. And this is an important point because it will mean that we will have to use the calorimeter, which doesn't saturate, for our centrality determination, and we won't be able to use the tracking detectors. So that was about the LHCb detector. I will move now a bit to introduce physics of heavy ion collisions. So just in general, since this was mentioned already, the goal to make collisions of relativistic heavy ions is to basically understand how the evolution of a lead-lead collision or ion-ion collision. We know that there are several steps that they go through. First, you have the initial state, so basically the two nuclei that have some structure modified with respect to protons. Then you have hard scattering, where the high mass particles are produced in general, and then you have a QGP formation. Then this QGP formation expands, and you have here a hydrodynamics taking place. This will produce all these correlations between the particles that we see in the final states. And finally, you have a hadronization of the quarks and gluon into hadrons and the freeze out. So we want to first characterize the quark gluon plasma and measure its properties. And lately, there have been these observations of some phenomena that we were attributing only to QGP formation, let's say, and they are appearing also in small systems where we do not have energy density to have large volumes of QGP. So we want to understand these signatures and basically understand the evolution between p-ion and ion-ion collisions. So the first thing we need to do is to characterize these ion-ion collisions. Not all the collisions are the same, as you probably know. The geometry of the collision affects both evolution and also the observables that we measure. This is because the medium that is created is influenced by in particular by the impact parameter between the colliding nuclei, and this is the quantity that we call a centrality. And as an example, you have the flow measurements. So basically, this fluid can take information from the initial spatial anisotropy and translate it to an anisotropy in the momentum space of the final state particles, and you have this V2, which is basically the Fourier coefficient of these fluctuations of the elliptic flow, and you see that clearly varies with centrality. And other QGP signatures are like Quarkonian suppression are also affected, as you can see here. So this is a very important quantity. So what we want to know is this B, the impact parameter, but also other parameters like the M part, which are the participants. So the number of nuclei that basically cross the other nucleon, the number of nucleons, sorry, and then the number of binary nucleon-nucleon collisions. This cannot be determined directly from the experiment, so we need to rely on a model. And what we do is to use MC Glauber model. This model is known to work well, especially in central collisions of large nuclei, and some problems start to appear in peripheral collisions, both because you start to have fluctuations, the lower the number of participants, and also electromagnetic interactions are important. But a good point about this model is that all the collaborations use this approach. So at the end, the measurements should be kind of comparable. So a snapshot about the model that we are using. So basically it's a stochastic model. We have the two nucleons as hard spheres, and we generate nucleus-nucleus collisions. And basically each collision we treat it as a superposition of individual nucleon-nucleon interactions. These nucleus move in straight lines, and they don't deviate even if they collide, and there is this condition for collision. Basically, there are two ingredients for this model. One is to provide this nuclear transverse density profile, which defines the shape of the nucleus. And then we have to provide the experimental quantity, which is the nucleon-nucleon cross-section. And this is extracted from measurements, and you have here a plot from a recent review that parameterize these measurements from, parameterize this quantity. So now we move more to LHCb. So what we want to do is to relate these Glauber parameters that we generated with experimental measured quantity. And for that, we use a mapping procedure. So you have here this sketch that represents that. Basically, for every average impact parameter or M part, you would have a number of produced charged particles in the experiment. Depending on that, you would have different collision geometries. So as I said, the best option for us is to use the energy collected in the ECAL. The reason is because we don't have saturation, and we cannot say that for the tracking detectors. And also for lead neon, where we do not have saturation in the velo, thankfully, it's better to use the ECAL in any case, because the energy doesn't depend on the position of the vertex. And as I said before, in fixed target, the vertex position is spread all over the velo. So basically, the energy of the ECAL is proportional to the number of produced particles, because it's proportional to the number of pi zeros. And we extract from data this quantity, the mean energy deposited per particle, to get a distribution similar like this. And this is what you have here for lead and for lead neon. We have to worry a bit about selecting well our events to do this measurement. First, at low energy, low centrality, let's say, events start to get dominated by electromagnetic interaction. So we can only consider energies larger than these values to do our Glauber fit, as you can see here. You see the great difference between the Glauber model and the data in these low energies. And also in LED Neo, we have to worry about some background interactions. So this is what you see in this plot here. There are two contributions of background. One is ghost LED interactions, and this is because we only use collisions where we have LED in bin 1 and an empty bunch in bin 2, but sometimes some ions can get debunched and go into empty bunches. So you end up having some kind of contamination there. Also, we have the possibility of having a collision very upstream the interaction region, because the gas leaks into the LHC pipe. So the good thing is that we can remove all these contributions just using that all fixed target interactions should not have any backward velo activity. Because all the particles go in the opposite direction. So after applying this cut, you have got this cleanup, which is very, very nice. Yeah, so now we need to fit the Glauber model to our data to extract some parameters. So the first point is to construct a model. And so from the MC Glauber, we extract the number of M part and N call, and we compute this N number of ancestors, which is something proportional to the particle emitting sources. And basically, this F is a parameter that we need to fit and tells us the relation between soft processes and hard processes producing the particles. Then we need to sample this N-ant onto a negative binomial distribution, which you have here. And basically, this is to construct a distribution similar to what we have in data. And this distribution also has some parameters. So at the end, we need to fit these two distributions. This actually is after fitting, but I don't have a plot before fitting. And yeah, you have here how we do this minimization for both LED and LED Neo. And yeah. And finally, when we have these distributions, we can segment our energy in centrality classes and then go to our Glauber model and compute the value of M part, N col, and B for each of these segmentations, let's say. And this is what you have here. So basically, the parameters of interest would be the mean of each of the values and also the sigma. And you can see that these values already from Glauber, there is some overlap between neighbors, between neighboring values. And this would be the same, but for LED Neo. Okay, the energy is much lower, so the energy collected in the ICAL is also lower as well. Yeah, so finally, we consider some systematic uncertainties that might be interesting to go into. Basically, first is to look into how much our determination depends of the centrality bins depends on how much we bin this histogram. So we bin it much better to get these values, but at the end there is some computational limit, but this uncertainty is small. And the rest are from this experimental parameter, also the fit fluctuations, and this statistical uncertainty from this the sampling on the negative binomial distribution. Also, we have to consider that for not peripheral events, we have this contamination from electromagnetic and interactions, and also important point is that the systematic uncertainties are smaller than the RMS that comes from the Glauber model. So it's not, they are not limiting our knowledge, let's say. So now I brought you two examples of that use this centrality determination. I won't discuss them in very much detail because I think they will be treated in future lectures. But well, in any case, you have here a measurement that we did of JPSI production in lead-lead collisions. And the goal of this measurement was precisely to distinguish between electromagnetic and hadronically produced JPSI, which you can have here in these two sketches that it can be produced in both kinds of interactions. And when you have a electromagnetically produced JPSI, generally it has much lower PT, so you can separate it using the logarithm of the PT distribution. And basically here we study if there is any dependence of this photo-produced JPSI with respect to centrality, which is quite flat, the dependence. The next measurement I want to show you as example is in lead neon collisions. So here, well, the JPSI meson is suppressed in low energy nuclear collisions with respect to D0. This happens already in proton-ion collisions due to nuclear absorption. But when you have QGP formation, in principle, you start to see an anomalous suppression of JPSI. So we wanted to see if we could see this anomalous suppression as was seen in lead-lead collisions by SPS. And yeah, basically you have here the ratio of cross sections plotted versus encol. And we fit it to a function that basically parameterizes this nuclear absorption. Basically, with our precision, the measurement shows that we are compatible with a nuclear absorption only scenario. So we don't see any anomalous suppression, at least in this data. So we are here to look into more heavier nuclei, yeah, than neon in case, because probably this anomalous suppression is more for larger encol, let's say. So that's all I have about ion large systems, and now I will talk more into small systems, which in the case of LHCb is quite a variety. So first, as I said, small systems are the core program of heavy ion collisions at LHCb. The reason is because we don't have any limitations in the centrality reach as we have for lead-lead, and all our subsystems perform optimally. Why do we want to look at small systems? Well, as I said, also to study this transition between these phenomena that we see that are QGP-like in small systems, and to see if there is some kind of connection between high multiplicity and low multiplicity in different systems. However, centrality determination is challenging. In proton-ion collisions, the Glauber model is not precise, and we are subject to fluctuations, also because we have no multiplicities, and for PP we don't even have an analog. So generally what is done here is to use event multiplicity directly. So for instance, the charged particles produced in an event to determine this quantity. However, this gives some complications. Okay, well, maybe we go for the questions later. Some complications, which one is which pseudo-rapidity region is used to determine the multiplicity, because this has been seen that has effect in some results. And also that the number of charged particles without any detector effects is a quantity that needs to be obtained, and it's not always available. So at LHCb, generally, we have been using we use generally Velo information because it has very good performance. So we kind of get rid of, we don't have to worry much about the detector effects on the observables. And also it gives us the best pseudo-rapidity coverage. So I don't know, maybe I go over the question in the, well, I cannot reach the chat. Well, anyway, we go over the question later. Yeah, so I brought you here an example of a measurement that where we do an activity class determination using the Velo, as I said. So I think this is also a topic for a future lecture. So we won't go into much detail, but basically here we want to search for ridge-like structures in high multiplicity proton-lead collisions. These were seen early by CMS, even in PP collisions, and they are assigned. They were always a sign of collectivity and considered as a QGP signature. So basically, to determine the occupancy here, we use the number of hits in the Velo, and we determine this class. So the problem of this is that it is not really a quantity, a physics quantity, but the good thing is that the number of hits of Velo, it's a quite raw quantity that is not subject to, for instance, reconstruction effects mostly. So it's quite safe to use, let's say. And we saw this small ridge structure both in the forward and backward detector configurations. So another example of studies with multiplicity that we do use the number of Velo tracks directly as a multiplicity estimator. And well, here you have the production of exotic particles, and this was aimed to provide to see if we can get information about the nature of this exotic candidate, which it's not clear whether if it's a tetraquark or a molecular state. This X3872. So basically, we measure this production versus I2S with respect to the number of Velo tracks produced in the detector, and the conclusions. We see this trend of decreasing of the ratio, but the conclusions are not very, like some models predict similar trends for tetraquark and favor this interpretation, but let's say that other models favor a molecule with this same trend. So this is still ongoing. This well, this is not yet closed issue. So yeah, those were a bit my examples of studies with charged particle multiplicity. I must say that in LHCb we started recently with those. So and what we generally have is more analysis, measure pseudo-rapidity and transverse momentum spectrum of different probes. So generally, our aim in this analysis is to study cold nuclear matter effects. So basically, these are modifications in the particle production yields in ion collisions with respect to PP. And these are the ones that are not linked to a deconfined medium. So basically, you take P-lead collisions, you assume you don't have any QGP effect, and you measure this quantity here, the nuclear modification factor or ratio between scale ratio between cross sections, and you see if it deviates from 1. There are many cold nuclear matter effects that are known. Some are final state effects, other initial state, depending on the time they act in the collision. initial state effects are generally treated with global analysis that parameterize these modifications with respect to PP, and this is done in nuclear PDFs. So you have here, for instance, the typical shape of this is taken from a nuclear PDF analysis, and you have this modification in the vertical axis, and this is basically the ratio between the PDF in the nucleus between the proton for a given flavor. This kind of global analysis need of experimental data as input, and also we need experimental data to characterize other cold nuclear matter effects not included in this initial in this modification of the partonic structure, let's say. So in LHCb, we exploit to the maximum our rapidity coverage. And this is because in the QXQ square diagram, which is basically the map of the PDF, we can reach regions not covered by other experiments. So you have that in the forward configuration in proton-lead, we can go to very low X. In the backward configuration, we can go in this band here at medium X, and then in fixed target, we can cover this high X region, which is also interested and not covered by the other LHC experiments. Generally, in this analysis, we aim to measure cross sections and the RP-LED with respect to IT and PT, and we have many analyses at LHCb. In this talk, I will cover those that I think are not covering future talks, which are light hadron production and pi zero production in PLED and PP. But also we have some analysis of light hadrons in fixed target collision. So let's start with the first measurement I will discuss a bit in detail. So as I said, we want to measure the RP-LED or ratio between PLED and PP cross sections. And here what we measure is prompt charge particles. So it's important to set clear the definition of particle that we measure. Here is the same definition that other experiments use, basically long-lived particles coming both from the primary interaction or without any long-lived ancestors. These are the list of particles, and for this analysis we used 5 TeV data. And yeah, you have here the acceptance in the center of mass system, and you see the effects of the boost that I commented at the beginning. So we get the RP-LED only in the common range. So how does this go? So basically, the charged particles are measured with long tracks, which you have drawn here in this sketch over the tracking LHCb tracking detectors. However, not all we are going to miss always some long tracks due to reconstruction and selection efficiency, and we have to correct for that. And also we are going to have some background tracks, which we have also to correct for them. These backgrounds are mostly fake tracks, which are tracks that our tracking system made up, which are not negligible especially in high occupancies. Mostly due to our tracking configuration, and also secondary particles, which are particles coming both from material interactions and daughters of long-lived particles. So this is a bit of an outline of the strategy that we take. Basically, we have to be very careful with these backgrounds because they are difficult to emulate with the simulation, especially in large occupancies. And they are not negligible, especially at large PT. We set a tight selection to tracks, actually using a neural network classifier for ghost tracks. And then we measure the selection efficiencies using calibration samples to not rely on the Monte Carlo prediction. And the remaining background after the cuts, we estimated both with simulation, but also with data using calibration samples with background and rich background samples. Another point of importance is that the reconstruction efficiency depends on whether the particle is a kaon, proton, or pion, for instance. And we don't have yet a measurement of these abundances in our acceptance. So we need to use a simulation that we validate with ALICE data in the central region. So this is an important point. And actually, this last point is what is going to make up most of our systematic uncertainty, as you can see in this table. And then we also have contributions due to the limitation of the samples of calibration that we have in, but this only affects boundary bins of the phase space. To improve the precision, the next step would be to use our PID information to measure precisely this pion, kaon, and proton contribution, which will affect this composition uncertainty. And yeah, here you have the results. I won't discuss them much because I think the aim is more the experimental techniques. But yeah, basically you have here the RP-LED. We see a suppression in low PT, quite a strong suppression, and this is more or less predicted and expected by the models. But in the backward region, we see a strong enhancement around, for PT larger than 1.5, let's say. And this is not predicted, for instance, by nuclear PDFs, and this points towards additional cold nuclear matter effects in this region. So I will discuss now about another analysis. So it's a bit similar analysis in its aims, but the experimental techniques are completely different. So I think it's very interesting to see. So basically, we measure a pi0 production. So the aims is similar to as the previous analysis, but here we are measuring a precise hadron species. So we can maybe disentangle effects from different hadrons and help us to understand this enhancement that that I just showed you. Pi0s decay to 2 photons mostly, so we need to use the calorimeter to reconstruct the photons. But actually, in this analysis, to have the best possible resolution, we use a technique where one of the photons is reconstructed with the calorimeter, and the other is reconstructed from an electron-positron pair that comes from interactions with the material. So basically, the photon converts, and tracking system detects this electron-positron pair. This gives us much better momentum resolution, but the statistics is lower, but this measurement is not limited by statistics. So we use these data sets here for PLED and PP. The energy of the PP reference is not the same, so we will need to do an interpolation, as you will see. A bit about the measurement techniques. So basically, we start by extracting the yields of pi0 in different transverse momentum bins and for the forward and backward configurations. The yield has typically this shape. Basically, you have the pi0 signal, the combinatorial background, and this Bremsstrahlung contribution, which is basically when one photon is paired with its own Bremsstrahlung emitted photon, one converted photon. So it would be an electron-positron pair that emits this Bremsstrahlung. After getting the yields for every PT, we need to correct by detector effects using a simulation. Of course, as before, we need to calibrate it well to correct for discrepancies with the data. And here, since the momentum resolution is not as good as for charged hadrons, we need to perform an unfolding iterative technique to correct for resolution and also the efficiency. Yeah, so here you have the measured cross sections in forward and in backward and forward, and for the different systems. And as I said, for PP, to get the RP-LED, we need to interpolate the results because we do not have a data at the same energy of P-LED. So this comes at a cost of a systematic uncertainty, but unfortunately, other systematics we have cancel when we do the RP-LED, and at the end we get quite a nice precision, about 6% in most beams. And these are the results. So basically, we have here the forward region and here the backward region. We observe a similar suppression in the forward as is predicted by the models, and also as we saw with charged hadrons, which you have here overlaid with points. In the backward region, however, we see a small enhancement that is not predicted by the models. But this enhancement is smaller than what we see for charged hadron. So this points towards that this cold nuclear matter effect is somehow stronger for protons or kaons. This could be one of the interpretations, since they are present in the charged hadron sample. So yeah, that's what's all I have about the physics result and performance, basically. I wanted to talk just a few slides about the LHCb upgrade, which, yeah,
I have
basically.
A quick question.
Sure.
A quick question about your previous thing. Yeah, right.
No, tell me. Yeah, I think we're fine.
What restricts your PT range here?
You mean the minimum PT? Is 1.5.
No, can you go above 10? Is it just statistically limited?
Well, I think it's also systematic is limited. I mean, I kind of remember I don't know if the problem is the resolution of the ecal, or yeah, no, clearly it's hard to go to larger in our acceptance.
Oh. Okay, thanks.
Yeah. Statistics, I don't think it would be a problem, because at the end, this is only a minimum bias sample that is very, I mean, you have a lot of pi zero produced in every event. So this is not the full data set, let's say.
Yeah, but you see the statistical error is pretty large at 9 GeV. So
yeah, but I think we could reduce that. The problem, the limitation there, I think it would be more the systematic. Even if the sample that we use here, is limited there, but yeah.
Systematic in the sense of track reconstruction between different.
Mostly the resolution of the calorimeter here, because here we have this reconstruction methods where we have one photon in the calorimeter and this electron-positron pair. So this,
I see. Okay, I understand.
The calorimeter, the energy is not easy, and sometimes you, when you have a very energetic pi zero, they tend to give you only one cluster in the calorimeter. So you have to, yeah, you don't know if it's like only one pi zero or yeah, you have some ambiguity there. So it gets harder at higher momentum, I think.
Okay, thank you.
Okay, well, if there are more questions now, what I have left is just the outlook. Well, I can go over the outlook, and which is going to be brief. So basically, we are now upgraded the detector. Actually, it's already mostly installed, and we are in commissioning phase. Basically, the idea of the new detector is, well, we upgraded most of the systems, especially the tracking systems. So, and also the PID detectors, but mostly the tracking. The idea is to move to to remove all the hardware triggers. So we will reconstruct the data online during data taking, and we will have possibility to have a much larger bandwidth. But all the detectors for that have to be much faster. And also, a very important point for the heavy ion program is that we install this SMOG2 system, which is basically a confinement cell. So this is upstream the velo, so it would be located more or less here. And basically when the velo closes, the cell closes, and we can inject gas that will stay only here. And this allows us to inject more pressure without disturbing the LHC vacuum significantly. And this means a 100 increase in the luminosity that we get. Also, the cell will allow us to inject other gases like hydrogen, oxygen, and deuterium. Hydrogen would be very important to get our RAA and RPA measurements. And also, we are working to also reduce the systematic uncertainties. And for instance, we are able to do a precise luminosity determination by measuring precisely the pressure in the cell. So yeah, since we are changing our tracking systems, we did some simulations, and we see that we are expecting to be able to reconstruct that to 30% centrality in LED. So the main factor here is that the new value is a pixel silicon detector, so we have larger granularity, and it can cope with the larger occupancy. And the limitation now at 30% will come probably from our downstream tracker, the SiFi, which is a scintillating fiber detector. And also we are aiming to reach full coverage with heavier gases like lead, like injecting argon while we collect lead. So yeah, and you can see here our expectation for our tracking efficiency, which is not terrible, let's say, at around 30, around this value of hits of the SiFi, which is more or less this 30% limit I talk about. And yeah, for the SMOG system, the idea is to have something like this. Basically, we will have in PV set a region where the SMOG collisions take place, the fixed target, and then the nominal PP collisions. And this aims to be able to take data simultaneously in both ranges. And this you can already see for the limitations that I showed you in the centrality limitation, the centrality determination, it would be very interesting. Give us much better control of the systematics. This plot here is actually already reality, is data, let's say, is one of the plots we got from commissioning. So you see that indeed the gas seems to stay in the cell, and we have these two independent interaction points, although this we still need to work a lot in the understanding the performance of the detector. So yeah, that's a bit it. This is just the summary, which yeah is mostly what I said. I am happy to take any questions. Maybe I can start with the ones in the chat. So the first is, what is the role of the Glauber model in centrality determination? Is centrality determination entirely driven by the measurement of charge particle multiplicity? Yeah, the thing is that you need when you talk about centrality, actually you are referring to geometrical quantities of the ion-ion collision. So for instance, this V is literally the impact parameter. So the charge particle multiplicity gives you the something similar to what you have up here, but you need some kind of model to do this translation, because yeah, this has to come from the phenomenology. I don't know if I've been clear enough.
Yeah, so So but if by centrality, suppose we just define it by this upper panel thing, right? That okay, multiplicity, top 10% multiplicity is my 0 to 10%. Now theorists will figure out whatever what event is, how it looks, right? So experimentally, then you define it only through the multiplicity, which is purely a measurement, right? There is no modeling involved, I guess.
I mean, this strategy is more or less what I discussed here for small systems, right? So basically, just we take the multiplicity. I think this is valid and this can be done, of course. But here you start to come into issues like which region of pseudorapidity you take to measure this multiplicity. Because, well, for instance, in LHCb, we have detectors in this range, but the other LHC experiments generally cover more central regions. So it is not clear that this, just making a distribution like this gives you results then in whatever quantity you want to measure that are fully comparable between systems. So I think that's one point there. But yeah, I mean, of course, it's something when you measure the multiplicity and you have to get rid of detector effects. You have to correct for your efficiency, which is not always easy. But once you do that, yeah, it's a measurement. Is reality.
Okay. Thank you.
Yeah, I think it's more like two different approaches, somehow complementary. Yeah.
I had a question. Which is kind of long, but we could start from your slide 18.
Yeah.
Okay, so now this kind of carries on with roughly the same question. In order to relate geometric quantities like the impact parameter to various experimental definitions of centrality classes, we'll have to use models such as these. Okay, but you're aware, I mean, all of us know these are just models and they need to be tested. Okay, so for example, when you start with this definition of the ancestors, then pick a negative binomial distribution, etc. Which parts of these have actually been tested? Whether these are, yeah.
Yeah, I think you're right. I mean, the reason to use Glauber is mostly because it has been quite well tested for in the most central region. So there are this is something that has been used a lot of years, and it seems that this kind of fluctuations, this influence, it's more or less suppressing the central region because you have so many participants that, yeah, you don't have any, yeah, the model works, let's say. As you said, this is a model and needs to be tested, yes. And yeah, I mean, there are measurements of in peripheral netlets. It's very likely that this is not working very well. Actually, the region where we are using it for, but there were some measurements from Atlas and CMS trying to calibrate this with set boson production, and they were seeing some deviations from the Glauber estimation and this calibration from physics, let's say, especially in the peripheral region. So, I mean, you are very right.
Yeah, so it strikes me, to continue with this, it strikes me that with your proton nucleus, especially with the proton nucleus measurements, you're in a wonderful position to test, models of initial state, like MC Glauber is used. Sometimes some CGC-based model is used, and you're right there. You should be able to check these questions if you have the right variables to look at.
Yeah, I must say that these are studies we are not very advanced in at LHCb, because let's say we started our community is growing, but that is definitely something very interesting that Alice, for instance, has looked at it in detail. And I mean, we could do more there. But one point there is that when you get the Glauber model or Pillet, the uncertainties and the spread of these geometrical quantities is huge. I mean,
right. So that gives you a better laboratory to check these.
Yeah.
If there's no other question immediately, can I ask a second question?
Of course.
It's a different thing. So let's go on to, I think I missed what went on in, I think it was slide 34.
34. Yeah.
Yeah, right.
Here.
So what's the statement here? Can you go over it again?
Could you repeat? Sorry.
Could you just summarize what you're trying to say with these plots? So and the plots went by too fast for me to follow.
Okay, sorry. Yeah. So basically, what we measure here is the nuclear modification factor. So for charged particles, right? So this is a measurement that mostly all the experiments did, and actually is when you do it in lead-lead collisions and you get the RAA, you see this very strong suppression that it's an indication of quark-gluon plasma, no? That principle comes from jet quenching. In Pillet, what you want to do is to look at the cold nuclear matter effect, so modifications of the that, let's say, are not linked to QGP, to have more or less of a baseline. And in LHCb, since we can go here in more forward region, we start to go lower in X, and we have this stronger suppression that is linked to shadowing, or in the color glass condensate, saturation, basically. Then in the backward region, we see this enhancement, which is generally known as Cronin effect. That's many experiments.
Right. So this is a large X that you're looking at, right?
Yeah, here is more a medium to large X, yeah, like 10 to the -2, 10 to the -1 here.
I see. Okay. That makes sense, because it's also the region where the structure functions were kind of not, the nuclear effects were not very well known.
Exactly.
So
yeah.
Okay. Thank you.
Yes. There is no yet. There are some ideas and around to explain this Cronin effect, but I don't think there is a conclusion, because many very diverse effects can explain it. I think.
Right. Thank you.
You're welcome.
So I had a quick question. So it's on slide 23, I think 23 probably, or 22. Yes,
This
23,
one?
this one,
Okay.
yeah. So you had made a statement which was something similar to this suggests that the main process is nuclear absorption. Can you just say a few words about that, because I missed the main.
Yes. So okay, basically here we are looking at lead neon collisions and proton neon collisions. So here we are at low energies, and we know that the J psi there is a suppression of the production of J psi versus D0 when you go to a larger number of binary collisions, let's say, and call. And part of the suppression comes from nuclear absorption, which is basically that once the J psi is formed, it interacts with the nuclear with the remnant of the nuclei. So this is an effect that doesn't appear at LHC because the energy is just too large, but it is here because the energy is lower and also was in SPS energies. So this effect generally has more or less like a power law. And this is what is fitted here. And we see that more or less this model already fits this trend that we see. So if we had a QGP, what we would expect, or at least what SPS saw, was that at some point this slope would get more pronounced. And this would be the indication of a QGP, let's say, which is still not clear if it was a QGP or other thing, but yeah. Here, I mean, it's hard to see because this large, the largest points we have is not very precise. So, I mean, you can fit it more or less with everything. So, yeah.
Okay, yeah, thanks. And now it's clear.
Yeah, we really want to do this with lead argon to see the larger encall and to see if we can reduce also the uncertainty bars to get more precise.
Thank you.
Any more questions?
Yes. Yes. Do you have any more questions? Or Alicia, I think we can kind of stop the recording and see if there are any questions that people don't want to be recorded.